and share sound as well. There we go. Right, okay, so PD. For those who know about it, always worth having a refresher. For those who don't, if you want any more information, just give me a shout. I'm quite happy to jump on another Teams chat and we can go through it in a bit more in depth. Or if you want, come visit IPEC. It's a really friendly company based in south of Manchester in Stockport. Always worth coming to see. Okay. This is really to say there's nothing new about monitoring. You know, we've been monitoring the environment for ages, and whether that be a canary in a cage to test for gas or a gas monitor when you're doing confined space, you adapt technology, and it's always important to monitor before you go in. And this is no different. You know, the technology has moved on, but the principles remain the same. So what we're going to do, we're going to have a quick refresher about what is PD, very quick, and then we're going to talk about how it applies to real life. Safe substation entry, you know, going in there, and again, then looking at the life cycle of substations and how PD can be used throughout its life cycle. Then we're going to look at different types of monitoring systems, the hierarchy, the pros and cons, and what you should be looking for. But we'll start actually with one of the things that David was mentioning, hierarchy of controls. And you can see at the top, you know, physically remove the hazard, working dead is elimination, and that's the best bit. But as you heard from David, you can't always do that. So you work down this with hierarchy of controls and you try to substitute it, or then engineering controls. And where PD kind of sits is at the engineering control and the administrative control, because ideally, you know, it gives you a way of understanding what is going on without being in front of the hazard, because PD is detectable whilst it's live, but non-intrusively. So you are away from the hazard. But even with all this technology and all the things you're going to learn today, there's still a residual risk. And going with that adage of going home safe, you know, no matter what the residual risk is, your PPE, which is the last line of defense, should always be on. And there's some really, really good documents to help us. So you've got here quite a comprehensive document, Keeping Electrical Switchgear Safe, free to download. You know, read it, please. You know, it's great to have it, but it's even better to read it. And you can see here, there is a small section of PD in it about non-intrusive and how you do it. It's not a very big in-depth piece, but it starts the conversation. But we're also starting to see people looking at the associated risk. So here you've got Aviva. So again, loss prevention. They're about not writing out a large check to your employer saying, here you go, you've lost business continuity insurance. So they are actually saying, do PD testing and do it regularly. There's a couple of FM Global are the same. They mandate it in their policies. It would be really worthwhile looking at your insurers and your insurance policy and just checking what they want and what they expect. There will be that standard of checking the fire alarms, checking the fire pumps, doing this, doing that. But actually, you might be in the documentation a requirement to do PD testing and monitoring. So we're going to go into what is PD, you know, electrical discharge that doesn't completely bridge the space between two conducting electrodes. Yep, okay. But really, it's what causes PD, which is the interesting piece here. It's all the stuff you don't want, you know, defects, damage, contamination, or installation. By having PD testing, you can detect early signs of deterioration. And again, going back to the canary in the cage, it wasn't that long ago that we would drive around and check our tyres manually. And now modern vehicles will actually look for defects, damage, a loss of air pressure in your tyres. So again, it is just a monitoring system to allow you to make engineering decisions, better engineering decisions. It doesn't remove the engineer. It means that we keep them safer and they can make better decisions. So, small video. Let's hope you can hear it.
What is partial discharge? Partial discharge, or PD, is essentially a spark that occurs in defects in high voltage electrical insulation. It's called a partial discharge because the discharge only partially bridges the gap between the conductors. The discharge may be in a gas-filled void in a solid insulating material, in a bubble in a liquid insulator, or around an electrode in gas. In high voltage cable systems, PD is commonly found in joints and accessories, where a defect or void exists. These are caused by incorrect installation or long-term degradation of the equipment. In switchgear, cracks and voids in insulating materials and components causes PD internally. Contamination on the outer surfaces or incorrect installation of insulators, bushings, and terminations will cause surface PD. Partial discharge is generally accepted as the predominant cause of long-term degradation and eventual failure of electrical insulation. According to research, 80% of high voltage failures occur due to asset damage caused by PD activity. PD activity can be monitored on in-service equipment to reduce these failures.
Okay, there we go. A little video just to bring it to life a bit. Again, PD gives you that indication of deterioration, whether it be from damage or installation or from contamination. And you're doing it non-intrusively. So you're doing it outside of the high voltage enclosure, which allows you then to have that separation between you and the conductors. Right, let's move on. Okay, right, a little bit more of theory. Okay, so you've got here the power curve. And what you've got here is the PD will occur on the rising and falling edges when the insulation breaks down. It's not always going to break down exactly at the same point, but it's going to be there or thereabouts, which means you get these blobs appearing, the 180-degree identification. So if you see that you measure the PD and you look for a lock on the phase plot, by getting that, you can then cut out false positives, because you're not going to get PD happening at 0 volts. So here, you're not going to get PD happening. So if you get things there, that gives you the identification that it's actually noise rather than PD. So the one thing that you need to make sure you have is the ability to lock onto the phase of the power, and so you can identify PD and separate it out from noise. So how do we do it? Well, we've got a couple of options. Current pulse, and that is for PD that's internal, so you get like an EMP, it impinges or it drives, goes down to earth, and so we're looking there for transient earth voltage. On the left, you've got the looks like a donut, the HFCT, goes around the earth strap looking for earth leakage from cables, and then here you're like a stethoscope, and that's your transient earth voltage detector. Acoustics, well, there we go, a small directional microphone. But with all this, you've got to make sure that the equipment and you're aware of what can cause false positives. Battery chargers, they've been a bane, where they can actually produce a ultrasonic signal that really does emulate PD, but it is across the whole of the phase plot, so you can actually detect it as noise. Neon tubes, Velcro can do it. So again, external electrical noise can set these things off. So it's really important that you understand what causes these, so that you can make engineering judgments before you go into the high voltage enclosures. And based on that, make sure you've got these two key features. Lock onto the power waveform. If it doesn't lock on, then you're going to get drift, because not every place is going to have exactly 50 hertz. And wave shape analysis, to look at what it finds, to make sure that it's PD and not a false positive. Okay, right, a little bit about substation entry. So we've learned a tiny bit about PD. Again, if you want some more in depth, please just drop me a line. We'll jump on a Teams call separately and we can do some more, or there are training courses available. Please, please, please wear your PPE, read your RAMs, and before you go in there, do a dynamic risk assessment. It's probable that no one's been in there in months. So look at it and have a does it look safe? Is the lock in place? Has it been vandalized? Is there on the roof a forest growing out there? Is it likely it's going to be damp inside? All those things which should give you the confidence to open the door. When you open the door, you're going to just turn on your PD detector and it'll listen for that crackle, the ultrasonic crackle, to see if it's like the canary in the cage, to see if it's safe to go in. If there's no ultrasonics found, then what you can then move to is look the transient earth voltage. So you find a piece of metal, and it could even be a fire extinguisher or a piece of metal on the metalwork door, and then you test for transient earth voltage. If you've got a clear on both, then at least you've given yourself a de-risking before you go in. But again, visual inspection, if you go in there and you find there's puddles everywhere because there's a leak, question, should you be going in before you get on with your partial discharge scan, and certainly before you go live into the HV assets. There is nothing wrong with not going in. If you've got a worry about it, go and seek advice. Go and talk to somebody. Go and say, actually, you know what? Perhaps we need some better inspections here. Perhaps we need some help. Perhaps we need to isolate. Again, the whole thing about this is going home safe. It's also useful for across the lifetime of your asset. So I did like this because it's just about the bathtub curve, and you do get here installation errors. So when you have new equipment put in, you've got that infant mortality piece in the failure rate. So installation errors, manufacturing defects, and by the time they come about and bite you by being PD and by having a failure, you're never going to be able to prove whether it was an installation error or a manufacturing defect, because the installer will blame the manufacturer will blame the installer, but there won't be the evidence because it will have been blown up. So again, if you've got something where you've got a new switchboard being commissioned or a new substation or just something happening inside there, test it. You've got nothing to fear about looking for PD. There shouldn't be PD there. Perhaps do it day 1, day 7, and day 28, just to make sure as it soaks in that you've not got PD early. And then you go to the normal life phase, where you're going in and in a good old MOT style, you're doing a PD survey. Probably once a year, but if it's critical, once every 6 months. There are people I know that do it every month, but then that's their choice. But as you get towards the end of life, you're going to start getting age obsolescence. You're going to start getting equipment wear out. And it's not just about the fact that you're trying to monitor the failure or the potential failure. It's also the consequence of failure. The equipment you're monitoring is not readily available. You can't just pop down to B&Q or Screwfix and pick it up. It's 3 months if you're lucky, 9 months if you're after a substation. So again, it is giving you that early warning and monitoring the situation. And when you find something, when you find PD, the question is, well, now what? And then it's the increasing that monitoring to track the rate of change. It's when you find it, or when it's detected on your handheld, then you can have a look and you can start seeing the surface tracking, the carbonization. You know, you can look inside the HV cubicles, and then you will find the telltale signs. For those of you that are on LinkedIn, have a look. I posted something this morning. It's an international site where they've found PD. Again, it's partial discharge monitoring. Because it's non-intrusive, because it's done live, you can do it quickly and you can narrow down your focus to where you need to be putting your engineering effort. And so when you do have to go intrusive and you've got all your safety measures in place and you've got your PPE on, you can then actually identify it quicker. And if you're not monitoring, you're just guessing. You know, you're just waiting for it to happen. And here is a flashover. Would have been absolutely identifiable by PD monitoring, and you would have seen it emerge, and you'd just seen it get worse, and you'd just been able to do something about it. Instead, now you've got a really big problem. Okay, right. Options. On the right, you've got the handhelds. Other handhelds are available, but I like these ones clearly. On the left, you've got permanent. Advantages to both. The PD instruments, they're ideal for substation entry. They're costing you around about £5,000. They're great for doing a survey. The downside is that you'll only get the results as they are there and then. So if you go in once a year, that's it. Once a year, that's what is happening. Partial discharge has a relationship to humidity. So yes, you should keep your substations dry, but if it's raining, you're going to find more PD than if it's not. So again, potentially on the critical stuff, you look at permanent monitoring. Equally, there is this crossover. So you're going around your substations, you're looking for PD with a PD detector, and you find something. What now? When's my next shutdown? Do I need to? Well, actually, what you can do then is you can pop in a portable monitor, and you can put that in. They are available for rent. You can get them elsewhere. PD detectors are available for rent, actually. And you can then monitor it and see the rate of change. And then you've got the facts and data to go to your managers, to go to procurement and say, we're going to need a shutdown. It's getting steadily worse. I'm now getting more worried. Here's the facts and data. So again, they do work hand in glove, but start off with a detector, get some training, and de-risk your site. For permanent PD monitoring, you're far better off putting the sensors internally. It's a bit like trying to listen to a neighbor having an argument with a glass against the wall if you're trying to do it externally, or you're trying to use the air gaps. So here we've got two setups. You can see Around the cable, HFCT. You can see here the ultrasonic and the TEV probe here, exiting and going to the permanent PD monitor. There's a couple of places in the UK that are now starting to put these in as they do their shutdowns, as they do their maintenance, and then it'll link to the handheld, but then they can also put it directly into the monitor. And again, you don't need to have potentially one monitor per substation. You can rotate them around on your less critical ones. There are various ways of doing it. But all that needs to have really good data analysis. If you're collecting data and you need to be able to look at it and then analyze it. So whichever system you buy, if it's a permanent system, make sure that it is actually reporting to you what's going on. You can see on the picture there, it draws you to the red. Red is never good. Red is always bad. So you can see there that there's something happening in Manchester Road that needs your attention, and it's coming out of the HFCT. Again, make sure it's configurable so it sends you the emails, sends you alerts. Other systems are available, but have a look at the one which suits you. Make sure that it can work alongside your data. You've got here the PDD Pro. Now, obviously, I'm trying to get these out there, but again, look at what you're getting. Look at how it separates out PD from noise. Look at the sensors. Again, you push a button and it takes a screenshot. Why is that important? Because then you can put it into your report and it converts engineering into reports. You can record it and it's very, very good at reducing noise. It will remove noise completely just to leave a PD plot on there. And here's things that we find, so you don't do this intrusively. You can do a substation in around about half an hour, really. If you want to do it in a bit more depth, about an hour. And then if you find something, then you can concentrate on that area. But here you go. You can see when we've found things, you open up and you find that the nitric acid from the PD has damaged the insulator and leaves the residue. It then points you even closer to where you need your engineering effort to go. Customer feedback, again, plug and play. And James O'Neill ESS, you can hire them if you want to try before you buy. And he has several different brands, not just IPEC. So again, try before you buy. See which one you're comfortable with. And here's one posted by Dave. You can see it's in tandem. Why this is important, actually, I really want to labor on this. A zero result is a great result. It gives you that confidence that actually for the next 3-6 months, we're okay. It's like you've health check. It's like your MOT. Here, what you've got is you've got it in tandem. You've got the sensors going to the monitor unit, as well as is using the actual handheld. But equally, even people like Dave find PD. And you can see here, this was very recently. You can see the at the bottom here is the portable monitor. And then you can see the cables going there. And then here we've got the likely culprit. So very early PD activity on a supercritical site for BT. What does that mean? It means they can do something about it. It means that you can then take an engineering decision based on severity. You can then say, right, do I need to do it now, next week, a couple of months? Do I monitor it? Do I need to do anything at all? But it gives you the knowledge to take engineering decisions.